sewer gas, sour gas, stink damp. Or if you really want to strip it down to the raw chemistry, hydrogen sulfide, H2S. We have a lot of names for this stuff, and I feel like for most people, you hear those names and your brain just shortcuts to one specific thing.
Rotten eggs.
Rotten eggs, exactly.
It's the universal signifier, isn't it? You catch that whiff of sulfur, your nose wrinkles up, and you immediately know something unpleasant is nearby.
Right, it's the classic prank smell, or maybe bad day at the wastewater plant, a volcanic vent if you're out hiking. But, in looking through the research you pulled for this deep dive, I'm realizing something.
What's that?
That focusing on the smell, that rotten egg warning, is actually a huge mistake.
A fatal one, potentially. It is a massive paradox, and honestly, it's one of the most dangerous misconceptions in industrial safety.
How so?
The one thing everyone thinks they know about hydrogen sulfide is the smell, but relying on your nose, it's the single most dangerous thing you can do.
That is a terrifying thought. So you're saying our built-in warning system is basically lying to us?
Worse, it betrays you, right when you need it most. And that's really the mission of this deep dive. We need to unmask this chemical.
Okay.
We have to move past the stink and understand this is it's a ubiquitous industrial threat. It's a biological hijacker that shuts down your cells, and it's a destroyer of metal that can literally crumble infrastructure from the inside out.
And it's not niche either. We're talking energy, waste management, agriculture, even just nature itself.
It's everywhere.
So let's unpack this silent killer. Where should we start? Maybe the physics of the threat. When we talk about H2S in the air, what are we actually dealing with?
So at its core, hydrogen sulfide is a colorless gas. You can't see it coming. And of course, it's highly flammable. But if you take one thing away from the physics side, it has to be the density.
The density.
It has a vapor density of 1.1 teen.
Okay. Vapor density. For the listener who hasn't been in a chem lab since high school, break down what 1.1 teen actually means in, a real world scenario.
It means it's heavier than air. Air is roughly 1.0. So think about natural gas or methane. If those leak, they tend to rise.
Right, they float away and dissipate.
Exactly. H2S does the opposite. It sinks. It hugs the ground like dry ice fog at a concert.
So it's actively hunting for the low points.
Precisely. It flows almost like a liquid. It'll settle in trenches, bell holes, cellars, manure pits, the bottom of a tank.
It creates these invisible pools.
Death traps, really. You could be standing on a platform, breathing fresh air, drop a wrench, bend down to pick it up, and put your head right into a lethal concentration.
That's a chilling image. The idea that your waist is safe, but your knees are in the danger zone, and you said it's flammable too.
Oh, extremely. And it has this frustratingly wide explosive range. We talk about LEL and ULL, lower and upper explosive limits.
Okay.
For H2S, it'll burn at concentrations as low as 4.3% all the way up to about 46%.
That's a huge window. So almost half the air can be gas, and it'll still ignite.
Right. It's incredibly volatile. And here's the kicker. Even if you survive the explosion, the combustion product itself is dangerous.
What do you mean?
When H2S burns, it reacts with oxygen to create sulfur dioxide.
Which it's also toxic.
Highly toxic. It damages the lungs and respiratory system severely. So if it burns, you're essentially just trading one poison for another.
Okay, so it burns, it hides in low spots, it's invisible. I want to circle back to the smell, though. We started by saying relying on your nose is a trap.
Huh.
Why? I mean, if it smells that bad, shouldn't that be a really effective alarm?
At low levels, sure. If you're talking about tiny, tiny amounts, 0.0005 to maybe 0.13 parts per million, you smell it. It's distinct. But this gas plays a biological trick on us.
That trick.
It causes rapid olfactory fatigue.
Olfactory fatigue. So your nose just gets tired of it. Like when you stop smelling coffee after being in a shop for too long.
It's much more aggressive than that. Once concentrations hit around 100 ppm, which, by the way, is the level considered immediately dangerous to life and health, IDLH.
Okay, 100 ppm is the magic number.
That's when the gas effectively paralyzes your olfactory nerve.
So right when it becomes lethal, it becomes odorless.
That's the mechanism. You might smell it for a split second and then nothing. Silence. You think the gas is blown away or the leak has stopped?
But really, the concentration is just spiked.
And your sensors have been cut.
That is just incredibly deceptive.
Yeah.
Did the research explain how that happens? Is it just overwhelming the system?
It's actually more specific. There was a Johns Hopkins study that really dug into this. They found a specific protein called CNGA4 plays a key role.
CNGA4.
Okay, think of it like a safety plug or a circuit breaker. When the odor receptor cells in your nose get bombarded with this intense sulfide signal, CNGA4 just steps in and plugs the receptor.
It physically stops the signal.
It stops the electrical signal from getting to the brain. The phone line has been cut.
So your brain literally stops receiving the data.
Information flow stops. And you walk forward thinking you're safe, straight into the danger zone.
That biological mechanism is fascinating, but it leads us right into what this stuff does to the rest of the body. You called it a biological hijacker. How does it actually hurt us?
Well, it's frighteningly similar to hydrogen cyanide.
The classic spy movie poison.
Exactly. H2S works in almost the exact same way. It targets the mitochondria in your cells.
The powerhouse of the cell. I remember that from high school bio.
Right. Specifically, it inhibits an enzyme called cytochrome sec oxidase. Now, this enzyme is absolutely crucial for letting your cells use oxygen.
So it's not that you can't breathe.
No, you're breathing just fine, but your cells are suffocating. It's called cellular asphyxiation.
Wow.
Your lungs work, your heart pumps blood, the oxygen is delivered, but the cells can't process it. It's like delivering food to a house where the doors are welded shut.
And I imagine that hits the organs with the highest oxygen demand first.
The brain and the heart, immediately.
And what does that look like? I assume there's a whole spectrum of damage.
There is. At low or chronic exposures, you get what the industry calls gas-eye.
Gas-eye. That sounds unpleasant.
It feels gritty. The technical term is keratoconjunctivitis. It's painful, blurred vision, extreme sensitivity to light. But at high concentrations, we see something else. A phenomenon the sources call the knockdown.
The knockdown. That sounds bad.
It is. We're talking about concentrations above 7 ppm. At that level, unconsciousness isn't gradual. It can happen after just 1 or 2 breaths.
1 or 2 breaths, that's instantaneous. You wouldn't even have time to realize something is wrong.
Survivors often describe it as being hit by a sledgehammer. The respiratory center in the brain is paralyzed. You just drop. You stop breathing. And if you aren't dragged out immediately to fresh air, death follows within minutes.
And even if you survive a knockdown, the sources mentioned it's not always a full recovery.
No. That lack of oxygen to the brain, even for a short time, can leave scars. Lasting neurological deficits, motor function issues, even psychological problems like depression and anxiety. It changes people.
It's a heavy toll. Now, we've talked about the gas itself, but where does it all come from? I mentioned volcanoes, but I assume most of us aren't dealing with that.
Unless you're a very adventurous tourist, no. But yeah, nature produces it. Volcanoes, hot springs, and bacterial decay. Manure pits in agriculture are a huge, often overlooked risk.
And industrially.
It's a major byproduct of oil and gas extraction, what we call sour gas. It's also huge in wastewater treatment and, as you mentioned, pulp and paper mills.
The craft process, right? That rotten cabbage smell.
That's it. But here's where it gets a little counterintuitive. We don't just fight this gas, we actually make it on purpose.
Wait, we manufacture the silent killer. Why on earth would we do that?
It has its uses. The Claus process, for example. We capture H2S from natural gas, then use it to produce elemental sulfur.
And that sulfur goes into what?
Fertilizer or rubber manufacturing. It's also used to produce heavy water for nuclear reactors and in some specialized lubricants.
So it's a classic double-edged sword. Essential, but deadly if it gets loose.
That's the balance we live with.
Okay, let's pivot to the infrastructure side. We've covered what it does to the human body, but you said it's a destroyer of metal. How does a gas break steel?
It does seem unlikely, doesn't it? But this is a massive issue in the oil and gas industry. H2S causes a specific type of failure called Sulfide Stress Cracking, or SSC.
SSC. How does that work? Is it like an acid just eating away at it?
It's more insidious than that. When H2S corrodes steel in the presence of water, it releases atomic hydrogen.
Not hydrogen gas, but individual atoms.
Tiny little atoms. They're small enough to migrate right into the metal lattice, the crystal structure of the steel itself. They burrow inside.
And what do they do in there?
They create internal pressure. They make the steel brittle. So a high-strength steel pipe that's under pressure can suddenly just crack. It snaps rather than bends.
That sounds like an engineer's worst nightmare. You can't even see it happening from the outside.
It is. That's why they have a Bible for this. It's the standard NEC MR0175, also called ISO 15156. It dictates exactly what metals you can use in sour environments.
So you have to follow the rules, or things will break.
Period. But there was another material threat in the notes that caught my eye. Pyrophoric iron sulfide. That sounds like a spell from a fantasy novel.
It basically acts like one. This is a booby trap that nature builds inside storage tanks. A booby trap. How?
Okay, picture this. You have a steel tank holding sour crude oil. The H2S in the oil reacts with the rust, the iron oxide on the tank walls.
And it creates iron sulfide.
Right, a black scale. Now, as long as that scale is wet, it's stable. No problem. But let's say you drain the tank for maintenance, you open it up.
And the scale starts to dry out.
And pyrophoric literally means fire-bearing. When that dry iron sulfide scale hits oxygen in the air, it reacts. It generates its own heat.
It spontaneously ignites. No spark needed.
No external ignition source. It just gets hot and burns. And if there are any flammable vapors left in that tank, boom. That's why keeping things wet during cleaning is such a critical safety procedure.
That is just wild. Okay, so we have a gas that blinds your nose, drops you in seconds, cracks steel, and sets rust on fire. How do we even defend against this?
Well, since we've established the nose is useless, technology is the only answer. You need electronic detection.
Sensors.
Exactly, but not just any sensors. You have electrochemical sensors, the standard personal ones, but they can get poisoned. You have metal oxide semiconductors, MOS sensors, which are more robust.
Yeah.
And for big facilities, they use open path detectors that shoot a beam of light across a perimeter.
And placement matters. Right. Going back to that density issue.
Crucial point. You put a smoke detector on the ceiling because smoke rises. If you put an H2S detector on the ceiling, you're measuring clean air while workers below are dying.
So they have to be low.
Typically 12 to 18 inches from the ground or the grating. You have to catch the gas where it settles.
That makes perfect sense. So detection is step one. What about getting rid of it?
Engineering controls, we can scrub the gas by running it through caustic soda. We can even use biotechnology. Yep, a bacteria called thiobacillus literally eats the gas. It's common in wastewater plants.
Bacteria that eat poison. That's amazing.
And in oil fields, they inject chemicals called scavengers into pipelines to trap the molecules.
So we have robots, chemistry, and bacteria on our side. But it still comes down to the people on the ground, the human element.
And this is the most tragic part of the data. When we look at casualty reports, we see a recurring pattern. A huge number of fatalities are would-be rescuers.
The don't rush in rule.
Exactly. A worker goes down, it looks like a heart attack. A colleague's human instinct is to run over and help.
And they run right into the same invisible cloud.
They take one breath and they drop on top of the first victim. Then the third person sees two people down. It's a chain reaction of tragedy.
It really weaponizes our empathy against us.
It does. That's why training emphasizes you never, ever rush in without protection. You have to fight every instinct you have.
And what does that protection look like? A dust mask isn't going to cut it.
Not even close. For low levels, maybe an air-purifying respirator with a specific cartridge. But if the level is unknown, or above that 100 ppm IDLH threshold,
You need the big guns.
self-contained breathing apparatus. SCBA. Positive pressure. You need your own air supply on your back, just like a firefighter.
And if an alarm goes off, the protocol is what?
Evacuate immediately. But you have to know which way the wind is blowing. You look at the windsock. You move upwind or crosswind. If you run downwind, you're just racing a gas cloud you can never outrun.
And someone is overcome.
If you have the gear, get them to fresh air immediately. The medical treatment is high concentration oxygen. It's critical. It helps displace the sulfide from those enzymes we talked about, giving the cells a fighting chance.
It really is a battle for oxygen at the cellular level.
It is. Time is absolutely everything.
So to wrap this up, we've unmasked the silent killer. It's not just a bad smell. It's a chemical that blinds your senses, drops you in a heartbeat, destroys your equipment, and could even blow up a tank.
It's a formidable adversary. It requires total respect.
But before we sign off, there's one last thing I want to touch on from your notes. Something about regulations. There seems to be a tension there.
There is, and it's something for listeners to really chew on. Right now, OSHA, the federal regulatory body in the U.S., sets the ceiling limit for general industry at 20 ppm.
20 parts per million. Okay.
But the scientific community, specifically the ACGIH, recommends a threshold limit value of just 1 ppm.
Whoa! That's a massive gap, 20 versus 1.
It's a 2,000% difference, and it highlights a critical reality in industrial safety. Legal compliance does not always equal safe conditions. The science is moving faster than the law.
So we're learning more about the long-term, low-level effects, and the rules are struggling to keep up.
Exactly. The anxiety, the cognitive issues, it challenges us to look beyond the minimum requirements and ask what's actually necessary to protect people.
That is a sobering thought. Just because you're following the rules doesn't mean you're completely safe.
It's about doing the right thing, not just the legal thing.
Well, on that note, we're going to wrap up this deep dive. Respect the chemistry, watch the windsock, and for heaven's sake, don't trust your nose.
Stay safe, everyone.